Welcome to this episode of Grade 10 Math. We're bringing you 1.4 Factoring Trinomials by Decomposition!
Y'all ready for this?
Yup! So when expanding a product, such as 2x times x plus 4, we would use the distributive property. And that's where we take this piece out front and distribute it to each of the terms inside the brackets. So in this case, we have 2x times x. Hold up here. So 2x times x plus 4 is equal to 2x times x, which is 2x squared. And then that second product of 2x times 4, which gives us 8x. So that's the distributive property in action. And we've used that previously. We used that when verifying for our common factoring. Now we're going to be factoring other trinomials into products of two binomials, but let's check out how that could happen in reverse. That is, how we multiply two binomials together. If we were to expand this product, x plus 2 times x plus 3, we would end up using the distributive property twice. So when we have this x plus 2 times x plus 3, we can operate similarly to how we did up here. We took this first term and multiplied it to the other things. In the same sense, we can take this first term and multiply it to these other things. So x plus 2 times x will give us just that. So x times x plus 2. And that's the result of, again, just that first distribution. But then we're also going to multiply x plus 2 times this 3 over here. So we'll have 3 times x plus 2. So at this point, we've distributed once. But we have to do so again, because each of these is still a little bit factored. So in this first one, we'll have to take x times x, which gives us x squared, and we'll have to take x times 2, which gives us 2x. We also have to distribute the other one. We have to take 3 times x, which gives us 3x, and we have to take 3 times 2, which gives us 6. So at this point, we've doubly distributed. We've used the distributive property twice. Now there's no more multiplication to perform. We just need to collect any like terms. And the like terms I see here are these two, the 2x and the 3x. So finally, if I can make that plus look like a plus, we have x squared plus 5x plus 6. What we see there is that each term in the first binomial has to get multiplied by each term in the second binomial. That is, the x out of the x plus 2, both the x and the 2 have to get each multiplied by the x and the 3 in the second binomial. And we can use an acronym FOIL to ensure all those multiplications get taken care of. And through FOIL, we ensure that we multiply the first terms, the outside terms, the inside terms, and the last terms. There's your FOIL of FOIL.
So, if we take a look at this next example here, we can go ahead and use FOIL to make sure we're expanding the product of these two binomials and then simplifying, which means collecting any like terms. So following FOIL as the acronym, we're going to start by multiplying our first terms together. So we're going to go x times x, which is x squared. Next, we're going to go our outsides, which is x times 1, so that's going to give us 1x, right? We do not have to write that 1 there because the 1 is already implied. Next here we'll do our insides. So So our inside terms are the 4 and this x here, which multiply to give me 4x. And of course, we're going to multiply our last terms, which is 4 times 1 gives us 4. Notice that this x squared is what we got from multiplying our first, our x we got from our outsides, the 4x we got from our insides, the 4 we got from our last. So that's where we get the FOIL from, and we should have 4 terms. However, you'll notice that very often, as long as the binomials are set up with our x's first and our constant second, our OI terms can collect. You can combine those and simplify. So we're going to go ahead and do that. And make sure that our final answer is always in simplest form. So our x squared remains our x squared. However, we can combine our x and our 4x, and when we add those together, we get 5x plus 4. That's our final answer there. All right, for this next one here, we could do the same thing. So we're going to start with going our firsts, then our outsides, then our insides, then our lasts. And in my eyes, if you look at this sideways, it kind of looks like Maui's hook from Moana.
Oh, yeah. Yeah.
Yeah, I think that looks kind of cool. So, taking a look here, our firsts, we get 2x times x, which gives us 2x squared. Our outsides, we get 2x times 7, which gives us 14x. Our insides, we get negative 5 times x, which gives us negative 5x. And our lasts, we get negative 5 times 7, which gives us negative 35. We go ahead and notice that our OI terms again can be collected and then simplified. So we will end up with 2x squared. We will collect our two middle terms to give us plus 9x, and we have minus 35. Just something to keep in mind here. Why are these two terms alike? Well, because they have the same power on the variable, right? Both of them have x's, right? The 2x squared is not a like term because even though it does have an x, it's got two of them, where these guys, our 14x and our negative 5x, only have one, and our 35 has none, right? So that's what we're looking for when we're looking for like terms, is that they share the same variable with the same exponent, with the same power.
As always, don't forget you should be pausing this and trying examples as you go along. We're going to dive right into this next one, but if you want to pause, that's up to you. I'm going to FOIL this like you wouldn't believe. I'll be multiplying 3x and 5x, which will get me 15x squared. I'll also be multiplying today 3x and 2, which will get me 6x. I'll be multiplying negative 1 and 5x. And I'll be multiplying negative 1 and 2. Oi, what's this? Those seem like terms. So I'll still have my 15x squared, I'll still have my negative 2 at the end, but 6x minus 5x just gives me a single x. And of course I'm not writing that 1, I'm just writing it as x.
Notice if he did write that 1, that would actually be an E1 error, right, where you have not simplified your final answer.
Yep.
So make sure we get rid of those 1s, because they're implied.
I'm going to tackle this lastest example as well, where I'll multiply 4x times 4x, which will give me a 16x squared. I'll get 4x and negative 3. I'll get 4x and 3. And 3 times negative 3. Whoopsie daisy. Close call. And again, whoop, like terms. So I'll have my 16x squared. I'll have my minus 9, and then how do these combine? Negative 12x plus 12x. Oi, that's nothing. So that's 0 x's. I'm not going to write 0x in here, ox, because it's nothing. And that is how we expand and simplify the product of binomials.
So if you noticed, on this first example here, this guy, right, what we did is we multiplied those two together to get our x squared plus 5x plus 4, right? If these two things multiply to give me this trinomial, it can be said that each of these binomials are factors of our final product. Okay? And that's what explains to us in this little blurb here. Right? If two things multiply to give me something else, we can say that those two things are factors. Right? So if we know that that x plus 4 and the x plus 1 are factors of that trinomial, since that trinomial has factors, we can make sense and logically reason that that trinomial could then be factored. Right? We can break it down into smaller pieces, into the product of two or more things. And that's what we're going to start off with today. We are going to be factoring trinomials. Trinomials are often also referred to as quadratic expressions, and we're always going to have them in standard form. And now standard form is this form here. Notice that it is written in descending powers of x. So the term with the most x's goes first, followed by the term with the second most x's, followed by the term with the least powers of x, right? So here we always have our x squares followed by our x's followed by our constants. Now that would make it into standard form. And when we factor, we always want to make sure that our expression is written in standard form first. Okay? Now when we have standard form, you notice that we have these letters or these variables, a, b, and c. A, b, and c are just placeholders, because when we factor, we always have numbers or coefficients in its place. So taking a look at this first example, we have these three coefficients, right? 1, 3, and 6. Those would represent our A, B, and C values. So what we're going to do is we're going to look at this first example, and all we're going to do is we're going to determine what those A, B, and C values are for each of our quadratic expressions, or each of our trinomials.
So if you think you can get it from these definitions, just go right into it. Get all 4 of these. But if you want to see us go through this, here it happens. In this first case, we've got a single x squared, so a is 1. What did I just do? Our coefficient of regular x, not x squared, but regular x, is 3. So b is 3, and our constant term, c for constant, is 6. On this next example, our coefficient of x squared, which is right over here, is 2, so a is 2. B is the coefficient of x, which isn't just 4, it's negative 4. That is a necessary part of it. And our constant term, our term with no x's, our c value, is 5.
And on this next example, our coefficient for our x squared, our a is going to be 5. Our b, remember, is our coefficient for our x. Whoa!
What?
Do you see an x in there?
Honestly, I have no idea where it went.
Oh my gosh, dude, maybe if I zoom in?
No, it's not working.
Right, so if I do not see an x in there, I know that I will have 0 x's.
Oh.
right? So if I have 0 x's, my coefficient of that x is going to be 0. So my b value still exists. It just exists as 0.
Okay.
Does that make sense?
Yeah, no, I get it. Yeah.
Okay. And our c value, c for constant, is, boom, 9. And last but not least here, a is our coefficient for our x squared term. Our coefficient there is 1. So a is 1. B is our coefficient for our x term. And again, making sure that we're including that negative in that coefficient. So our b is -4. And c for constant, we end up with that +7.
Reason why you want these values of a, b, and c is because we're going to be using them to help us factor trinomials. What we're essentially going to do is take the steps of a double distribution in reverse. So instead of this being 1, 2, and 3, it's going to be the other way around. But I guess there's a 4 over here, which is factor form. We're taking those steps in reverse, which means we have to somehow turn this middle term into two things that add to it. But that could be anything. Like 5 could be 1 plus 4. It could be 7 minus 2. So how do we know that it'll have to be 2 and 3 in this case? Or in our next example, what do we actually do? We seek a very certain combination of numbers. In all cases, we're going to seek out factor pairs of a times c that sum up to b. You're right, a highlighter would be better. So for example, if we're given this particular trinomial, where we have a is 3, b is 8, and c is 4, we could say that a times c is 12. Therefore, we're looking for factor pairs of 12 that add up to 8. So looking at factor pairs of 12, that could be 1 times 12, that could be 2 times 6, that could be 3 times 4. Those are our options. 1 and 12 don't add up to 8. 3 and 4 don't add up to 8. How did that happen? Interesting. But 6 and 2 do. So here's our factor pair of 12, things that multiply to 12, but they add up to 8. How do we use that? Well, that tells us how to break up this 8x. This 8x will actually be rewritten as 6x and 2x. So in this first step here, that's what we've done. We've taken this 8x, we've broken it up into 6x plus 2x. At that point, we do a partial factoring. That is, we look at two separate components. We have this first half, and we have this second half. And we're going to take each one and extract its GCF only. So looking at 3x squared plus 6x, the GCF is 3x. And factoring just that will leave us with the 3x on the outside and inside the brackets, x plus 2. The second piece, the 2x plus 4, if we take the GCF of that, which is just 2, right, I was using highlighter, what remains will be x plus 2. That's a very, very key, critical step where we take each of these as separate components. They are all parts of the same expression, but they are treated separately just for a moment. And if we've done that step correctly, we'll notice that what we have left in brackets is actually same in both cases. They're both x plus 2, which means we can do another factoring out. We can say x plus 2 is common. And what does that leave us? Well, it leaves us the 3x, and it leaves us the 2 from there and there.
Will we always have our two bracketed binomials being equal, those two gray highlighted pieces the same every single time?
Why, yes. Yes, we will. That's a very key indicator that we have done something correctly. If they don't match, that means that something else has gotten a little messed up and we need to check back on that. But if they match, we're in a really good spot. Because if they match, then we can actually factor that piece out over here.
Oh. I find that very often if those two don't match, it's because we chose the wrong factor pairs.
That makes sense. That makes sense. So you'll want to be double checking your work all over the place. Any thoughts you have?
No, I think that makes sense. So we have the three kind of major steps here. So our first step is to figure out how we're going to decompose that middle term, right? We're essentially separating that oi that we combined before when we were foiling. The second step was to partially factor, right? We're going to pull out the GCF from the first half of our equation. We're going to pull out the GCF from the second half. And then lastly, we are going to notice that our two bracketed pieces should be identical. And then we are going to factor it out. So those are going to be our three kind of steps that we're going to follow. So why don't we give that a try? So we're going to do that over here. Now, it might be helpful for the first couple times that you're doing this just to kind of write your A, B, and C terms out on the side, but that's not necessary. So if that helps you, especially when you're just beginning, to go, well, what is my A term? My A term is my coefficient of my x squared, so that's 2. What's my B term? Well, that's my coefficient of my x, so that's 11. And what's my C term? Well, that's my constant term, so that's 15. So what I just did is I wrote out A, B, and C and what they equal, but I don't actually need to do this. I'm only doing this because I'm kind of new with factoring, and I want to make sure that I can see all of my work instead of doing it all in my head. So it's not necessary, but if it helps you, then by all means, go do it. All right. So when I'm doing factoring, remember that my first step was to break this guy up. We're going to decompose it. And we have to decompose it very specifically. So to do that, we're going to start by multiplying my A times C value together. So we're going to multiply 2 by 15. And when I do that, I get 30. Now that I've multiplied A times C, I am looking for factors of 30 that will add to give me 11. Right, so my factors of 30, I might want to start listing them out if I can't think of them automatically. I got 1 and 30, 2 and 15, 3 and 10, no 4s, but 5 and 6. And those are all my factors of 30. And as I go through them, I notice that not all of them work. In fact, only one of them will. 1 and 30 doesn't add to give me 11, 2 and 15 doesn't, 3 and 10 don't, but 5 and 6 do. So my first step of decomposing, oh, I don't want that color. I'm a really big fan of this purple here. Of decomposing that middle term, that 11x, I can rewrite that as 2x squared plus 5x plus 6x plus 15. And some of you might be wondering, well, when I write 11x as 5x plus 6x, does it matter what order I do that? Does it matter that the 5x comes first and the 6x comes second? Can I put that in whatever order I wish? And the answer is, it doesn't really matter, right? So regardless of what you do, you will still end up with the same result. Your work just might look a little bit differently than if you put them in the opposite order, but your final result will be the same, okay? So it doesn't matter if you have 6x plus 5x or 5x plus 6x, it will still end up in the same final answer. So that's step 1. The next step is to break this equation up into 2 separate pieces and to pull the GCF out of them. So in my first half of that equation there, my GCF is going to be 2x. So I'm going to pull out a 2x, and when I pull a 2x out of 2x squared, I'm going to be left with x. And when I pull out a 2x out of 6x, I'm going to end up with a plus 3. Now, in my second half of the equation here, my GCF is a positive 5. Okay? When I pull out a 5 from 5x, I'm left with x. And when I pull out a 5 from 15, I get a 3. And notice that this is kind of one of my checkpoints. That if I'm doing my work correctly, I should end up with both of those bracketed binomials being identical. And they are, so I know I'm safe to move on. So, the last step here is because I have my x plus 3 common in each of those, I can factor it out. And when I factor it out, I pull out my x plus 3, and I am left with my 2x and my plus 5. And that becomes its own separate bracket. And that is going to be my final answer. Another common mistake, since we're just kind of going through the example here, that people make is they forget to put a plus sign there.
Oh, yeah.
Yeah, and if they don't put a plus sign, that implies multiplication. And that actually changes the whole thing. So we always need to make sure that we either have a plus or minus sign there, depending on what is required for that specific example. But by far, that is one of the most common errors made in decomposition. Would you agree?
Oh, I definitely agree.
Yeah. So always be sure that you have some sort of plus or minus sign there. All right. I'm going to tackle the next example too, just because we're on a roll. All right. And we're going to do things a little bit more quickly this time because I feel like I'm starting to become a little bit more confident. You might be too. And that is the goal. So I'm going to write down my A, B, and C values. But this is probably going to be the last question that I'm going to outright write it down. I'm just going to do it so that we can see where those values are. So for my A value, I have 2. My B value, I have 5. My C value, I also have a 2. My first step is to take my A and my C value and multiply them together. So I get 2 times 2, and that gives me 4. Now I am looking for factors of 4 that add to give me 5. So I have 1 and 4, 2 and 2. And of course, only one of those will ever work out. So in this case, 1 and 4 will add to give me 5, whereas 2 and 2 don't. So that tells me how to break up my middle term here, right? So I'm going to rewrite this as 2x squared plus 1x plus 4x plus 2. And you might be thinking to yourself, hey, Miss T, why are you writing the 1 with the x there? If you would like to do so, as long as it's not in your final answer, that is okay. It's only your final simplified answer, your final answer, which must be simplified. But if in your work it helps you to write down that 1, by all means, do what you feel. All right. Next, we are going to break this up. We are going to factor out the GCF from my first 2 terms. And the only thing that these 2 terms have in common is that x. So when I pull that out, when I pull an x out of 2x squared, I'm left with 2x. And when I pull out of x from 1x, I am left with 1. Right? Another common mistake that people make is they go, well, I pulled out an x from 1x, so I'm only left with nothing. Which is incorrect. Right?
Completely false.
Yeah, when you pull out a value, so when I'm factoring out my x from 1x, I am dividing it out. And when I divide it, since my top and the bottom are the same, they reduce to be 1 over 1, right? Which reduces to be 1, okay? Next half of this equation, we are going to pull out a GCF, and that GCF in this case would be 2. And remember, I'm not just writing 2 there. I need to have a plus or minus sign. And since I'm pulling out a positive 2, I need to have a plus 2 there. Well, I pull out a 2 from my 4x, I'm left with x. And when I pull out a 2 from 2, I'm again left with 1. Oh, sorry. I'm left with... Yeah, that was a little slip of the tongue. When I pull out a 2 from a 4x, I am left with 2x there. Oopsie daisies. All right. Now I'm at my checkpoint. Are my 2 bracketed binomials identical in this case? Yeah! Yeah, oh, my voice went a little high there. Yes, they are. So I can factor them out because they are in common. So I have my 2x plus 1, and then what's left? Well, that's this x and the plus 2. So I have x plus 2.
Neat.
All right, do you think you can give it a try?
Oh, I know I can give it a try. Always try. So in this case, we've got A is 1, B is -5, C is -36. So we've got some negatives starting to run around here. And we have to think to ourselves, like, what is it we're going to do? And of course, in this case, what I'm thinking to myself is, what are factors of A times C that add up to B? Specifically, in this case, we need a factor pair of -36 that sums up to -5. That's what's going on in my brain. And we can run through options. Worth noting, something like 1 times -36 will give me -6. But so will -1 times +36. So there's quite a bit to look at. But if I run through pairs in my head, and I start thinking of 36 as these various things, just a regular 36 is that, or it's this, or it's that, or it's this, and eventually I stumble on something. I say -36 means one of those will be negative. In this case, I could say, ooh, huzzah, I've gotten a -5. If it turns out I wanted a +5, well, then I could just switch these signs around, and I get the same value with an opposite sign. In any case, the things we want are 4 and -9. How do I erase this? Eraser? Nailed it. So I'll say x squared minus 5x minus 36 still has an x squared, still has this -36. I don't like how I wrote that thing. But we'll also be subtracting 9x and adding 4x. And that is our decomposition step.
Very common mistake that's made here is that the signs for the -9x and the 4x are swapped, right? So very commonly you find the right factors, but when you write them down, ooh, you swap them. And so make sure that whatever you do, that -9x plus 4x, double check that it adds up to give you that value you're seeking.
Legit. Too legit. Too legit in order to quit. I'm going to partially factor this. I'm also going to partially factor that. So in my next line, my GCF of those first two terms is x, which leaves me with x minus 9. My GCF of those second two terms is a positive 4, which will leave me with x minus 9. And ooh, check this out. Both of these are involving an x minus 9.
Whoop, whoop.
Holler. And that means I can finish this thing off by saying, yeah, there's an x minus 9 that's common. And when I factor that out, it leaves me with an x and a plus 4.
Nice.
It is nice. Now here, I went with negative first, positive second. My next example, I'll do something a little different, just to see what happens. But hereabouts, where's black? We're seeking factor pairs of negative 20 that sum to negative 1. Feel free to take a moment, scroll down the list, see if you can come up with something. Oh wait, light bulb. Light bulb. I think that's negative 5 and 4. So I'll break this up, I'll decompose it, I'll have my x squared, I'll have my minus 20, but I'll also have a plus 4x and a minus 5x, because if I add those together, I'll get negative x back, and if I multiply 4 by negative 5, I'll get my negative 20. Cool. Partially factor this. Oops, that's not black. Which gives me an x as a GCF, x plus 4 remaining. I'll also partially factor this. But kind of critical is that if this term is negative, you're going to want to factor out that negative as well. So I'm not just going to factor out the 5, but the negative to go along with it. So negative 5. And that will leave me with x plus 4. Once again, I am super pumped because boom, boom! Those things are a match. Which of course means I can factor them out. I can factor out this common x plus 4. And that'll leave me with an x minus 5.
Nice. All right, last two examples. So we are now looking for factor pairs of our a times c, which is 6, that add up to give us negative 5, right? So things that multiply to give me positive 6. Well, that's 1 and 6 and 2 and 3. 1 and 6 give me 7, 2 and 3 give me 5. Well, those are all the factors of positive 6, right? Wrong! We have more factors. We also have negative 1 times negative 6 and negative 2 times negative 3, right? So even though we have a positive value, they can have negative factors. They would just both have to be negative. So this here still gives me negative 7 if I add them together. But...
Huh. You said but.
These will give me negative 5. So the factor pairs that I'm going to use are negative 2 and negative 3. All right. So 6x squared, and then I'm going to go minus 2x minus 3x plus 1. And now we're going to partially factor this. And so when I partially factor my first half of the equation, my GCF is 2x, which makes me left with, or leaves me with, 3x minus 1. And when I factor that second half, my GCF has to be negative. I also have to factor out that negative sign. So, I noticed that the only thing they have in common is a 1, so I'm going to factor out that negative 1, which leaves me with 3x minus 1. And hey-o, these two are the same. That's my checkpoint. I'm feeling good. I'm feeling fresh. I'm feeling fine. Now, the thing they have in common is that 3x minus 1. And what's left would be that 2x and that negative 1. So you have 2x minus 1 up in here.
That looks legit.
Yep. Sweet, 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 sweet.
Totes.
All right. Looking at this last one, we're going to cruise through it. A times C, we get negative 60. And we're now looking for factors of negative 60 that add to give me negative 4. And so as we go through them, feel free to think about them, see what you can find. I see negative 10 and positive 6, because negative 10 and positive 6 will add to give me negative 4, and negative 10 times positive 6 will multiply to give me negative 60. I kind of put that in a place I don't feel really comfortable with, so I'm going to scoot that over here. Alrighty. Now, I'm going to rewrite this, but instead of negative 4x, I'm going to write negative 10x plus 6x, and then I have my negative 5. Now, taking a peek at this guy, I'm going to factor out my first half of the equation. I find that my GCF of that first half is going to be 2x. When I factor out a 2x from 12x squared, I'm left with 6x. And when I factor out a 2x from negative 10x, I am left with a negative 5. When I look at the second half of my equation, what's my GCF? Well, there's no negative because this guy here is positive. Well, 6 and 5, what do they have in common? They only have a 1 in common. So in this case, I am only factoring out a positive 1. And I'm writing that positive 1 in this case because it'll help me down the road. So when I factor out a positive 1, I still end up with the same thing because anything divided by 1 is just itself. The reason that it helps me down the road is after my checkpoint where I go, yippee woohoo, I have the exact same thing, life is good. And I pull that out, I notice what's left. I have my 2x and I have my plus 1. 2x and my plus 1. And I needed that plus 1 to make sure that I include it down here. Every now and again, I don't want to say it's a super common mistake, but if you forget to put that 1 there, I don't say forget because technically it doesn't really change anything.
It's not fully necessary.
Right? And then you look and you're like, okay, what am I going to put in my last bracket here? And you go 2x and plus. And every now and then we see people go, well, 2x plus nothing. And there's not nothing there. There's always that hidden 1. So don't be silly and just go, well, times 2x. That would be just ridiculous. So we're going to make sure that we include that plus 1 because even if we don't write that 1 down here, we know it exists. Alrighty. If you look at the bottom here, there's some textbook suggested questions that you could give a go. And those are these ones here.
Just for some pro tips, don't forget that you can always verify your answer. If you just take your factored form and redistribute it, you perform that FOIL method of distribution, you can make sure that it actually multiplies to the trinomial you were given. And if it does, you're doing business real well. And if it doesn't, well then perhaps there was an error somewhere along the way and you just need to check that over.
You know what? That was a really great pro tip. Why don't we test it out with this last example to make sure it works?
Okay.
So, in my last example here, I got a final answer of 6x minus 5 times 2x plus 1. And I said that this answer is equal to this original trinomial, right? Because I've been writing equal signs all the way down and not forgetting them because that would just be a communication error. So to ensure that they're in fact equal, I'm going to go ahead and FOIL or doubly distribute to make sure that I'm in the same spot. So I'm going to write verify at the bottom here because technically it's not part of this work. I'm just checking my final answers are correct. So for this verification step, I'm going to FOIL. So my firsts would be 6x times 2x, which give me 12x squared. My outsides are my 6x times my positive 1, which gives me plus 6x. My insides gives me negative 10x. And my lasts give me negative 5. And notice, already I can see that these terms here are the same as those terms here. Which is, ooh, so nice.
Quite nice.
They're in a different order, but the order of addition doesn't really matter, or the order of that. So we're still good. And as I'm continuing, I'm going to collect my OID terms. So I'm going to collect and simplify. So I get 12x squared minus 4x minus 5. And I end up getting the exact same thing that I started with. So realistically, you could check every single one of your questions that you factored and make sure that you're right before you even hand in any of your work.
Nice.
All right, that's it for today. Peace out, homies.